Atomic orbitals. Schrödinger's first step in developing a model of the hydrogen atom was to devise an equation which is now known as the Schrödinger's equation that enabled him to calculate the shape of the wave associated with any particle. Then he went on to solve the equation for the specific case of an electron in a hydrogen atom. First, he found that waves would fit into the atom only for certain energy levels. That is exactly what is needed to account for the existence of energy levels. In other words, the quantization of energy follows naturally from the Schrödinger's equation because only certain waves are allowed. Then he found the mathematical expressions for the shapes of the allowed waves. These expressions are now called wave functions and denoted by psi. One of the fundamental principles of quantum mechanics tells us how to interpret wave functions. According to the Born interpretation, which was proposed by the German physicist Max Born, the probability of finding the electron at a given point in space is proportional to the square of the wave function at that point. Where the wave function has a large amplitude, there's a high chance of finding the electron it describes. Where the wave function is small, the electron will only rarely be found. Where the wave function is zero, the electron will not be found at all. Another very important difference between classical mechanics and quantum mechanics now becomes clear. In classical mechanics, we can predict the location of a particle, such as the location of a planet in its orbit around the sun. In quantum mechanics, we can predict only the probability that a particle will be found at a given location. And that is atomic orbitals. Have a great day.